Hi, I am Dr. M.D. Tanjil Sarkar, postdoctoral research fellow, Faculty of Engineering, Multimedia University. Here I presenting an overview of system identification procedure and perturbation signal. The presentation outline is the introduction, objectives, parametric identification in the time domain, non-parametric identification in the time domain, perturbation signal, and finally I will discuss a conclusion. Introduction. System identification is a methodology for building mathematical model of dynamic system using measurements of the system's input and output signal. The process of system identification is shown in figure 1, where the experiment design and data acquisition, then data processing, then model structure and selection, parameter estimation, then model prediction. If is the model is a good representation of the process, then it used for the model, or if not, then you go back to the level 1. System identification have two type, time domain and frequency domain identification method. There are lots of identification methods are available. Auto-regressive with exogenous inputs method, output input OE method. Identification, closed loop identification and open loop identification, parametric and non-parametric identification. System stability, stable and unstable system, system linearity, linear and nonlinear system. Objective. This paper provide a comprehensive synopsis of system identification technique with a focus on parametric and non-parametric approaches, along with the role of perturbation signal in enhancing the analysis. The paper explores the process of estimating system parameters by fitting mathematical models to observe input-output data. Challenges such as noisy data, model complexity, and overfitting are also examined. A different type of perturbation signals such as fixed spectrum signal, computer optimized signals are discussed. Parametric identification in the time domain. Figure 1 is the simplified problem representation on time domain, where u the naught is the input and y naught is the output is the noise. For a linear dynamic system, is y naught t equals to g naught q u naught t. Linear model structure for system identification in the time domain in the presence of noise. There are four types of model are available: ARX model, RMX model, OE model, and BJ model. ARX model is defined by parameters that describe the order of auto-recreation and the order of exogenous input. ARMAX model similar to ARX, the ARMAX model also include a moving average component. There may be a common denominator which is distributing the noise and the system with added CQ as an extra filter of the noise. OE model, it assumes that the system's output is a linear combination of past input and noise terms. VJ model. The VJ approach is widely used for analyzing and modeling time series data, including in system identification context. In this general model, the plant model is independent of the noise model. Non-parametric identification in the time domain. I think about the time domain strategy for non-parametric identification in which the system has a limited impulse response structure. Here are two approaches for figuring out the system's impulse response coefficient. Method 1. This method formulated as a winner of summation equation for a time series with n number of samples. The cross correlation estimate between the system input ut and the output yt as shown in equation 29, where g is the impulse response, m is the length of the finite impulse response model, and ru as the autocorrelation of u. The second method is the based on a process of minimization. The impulse response is identified by minimizing the prediction error according to reference 6. The signal involved can be thought of as uh, a process being realized if error and input are uncorrelated. The coefficient of the impulse response can be easily determined. Perturbation signal, fixed spectrum signal, those signals length and Performance index for perturbation signal values are clearly listed by reference 15, where PIPS equals to 200 U square RMS minus U square mean by half. U max minus U mean with percent. While URMS is the root mean square value of the signal, U mean is the mean value of the signal, U max is the maximum value of the signal, and U mean is the minimum value of the signal. These spectrum signals are periodic, being generated based on finite field arithmetic. Those signals have uniform spectra. PRB signals have been used in the identification of industrial process. The properties of fixed spectrum signal. PRB number of levels equals to 2 harmonics uniform spectrum, no harmonic suppression. QRT number of levels equals to 3 harmonic uniform spectrum, no harmonic suppression. Inverse repeated PRB number of levels equals to 2 harmonics uniform odd harmonics and zero even harmonics. PIPS 100%. Inverse repeated QRT, pure twice those of original signals. Number of levels 3, harmonics uniform at harmonics and zero even harmonics. Truncated MLT, number of levels 3, harmonics, non-zero harmonics are uniform and harmonic multiplies of 2 and 3 can be made 0. Perturbation signal, computer optimized signal. Computer optimized signals have optimization procedures which are usually automatic and user-friendly. A common form of computer optimized signal is multi-sign signals. A multi-sign signal is the sum of numerous connected residuals with several harmonics where the amplitude may be programmed. As a result, amplitude spectrum design applicable to this type of signal. The multi-sign signal is given by Rivera, UK equals to lambda summation root over a 2 a cos omega kt plus phi t, where lambda is the scaling factor, ai are the Fourier coefficient, ns is the number of harmonics, n is the signal period, t is the sampling interval, omega is the frequency of the ith harmonic, and phi I are the phase angles. Properties of computer optimized signal. DIV number of levels. Two harmonics, even harmonics can be suppressed. Optimization criterion power. DIT number of levels. Three harmonics. Harmonic suppression depends on harmonic specification. Optimization power. MLMA is number of levels. A small number of levels which is specified by the user. Harmonics. Harmonic suppression depends on harmonic specification. Optimization adjusts the comparative phase of the harmonics which minimize the crest factor. Multi-sign sum of harmonics, number of levels, practically infinite harmonics, the user specified harmonics optimization criterion adjusts the comparative phase of the harmonics which minimize the crest factor. Conclusion. This paper has provided an overview of system identification technique and the role of perturbation signal in enhancing our understanding of complex systems. System identification plays a pivotal role in various engineering and scientific disciplines by enabling the development of accurate mathematical model that capture a system's behavior. By employing parametric and non-parametric identification approaches, analysis can uncover hidden dynamics, estimate parameters, and model system responses with varying levels of complexity. It serves as a valuable resource for researchers and practitioners seeking insight into accurately characterizing system dynamics and behavior. Thank you. Here is the some references for this presentation.